Right. Yeah, so in the first question, we're given here overarching information that we can use for all of the questions A, B, C, D. In winter, a pond with a surface area of 27 square meters is covered by a 10 centimeter thick layer of ice, and the outside temperature is -5 degrees Celsius. So if we draw that scenario, say draw the cross-sectional area of the pond. Right. Right, so let's say that's the most cross-sectional view or 3D view of the pond. You have a surface area of 27 square meters, and it's covered by a thick layer of ice, 10 centimeters. So notice how your units, meters squared and centimeters, they're not consistent. So you have to, the safest is just to convert all your units to SI or base units. So we'll convert 10 centimeters to meters by dividing by 100. So this one, 10 centimeters will be equal to 0.1 meter. So that's a thickness of 0.1 meters or 0.10 if you want to carry over the number of significant figures to the converted thickness. The outside temperature is -5 degrees Celsius. So outside the frozen surface, you have T cold -5 degrees Celsius. And so let's go now to the first question. Assuming the water underneath is 4 degrees Celsius, so that's the temperature inside. So 4 degrees Celsius is of course warmer. So that will, let's say that's T hot is 4 degrees Celsius. Okay, so you can see from this scenario that you have a hot area. So the hot water underneath and the cold environment above, you have this difference in temperature. So heat will be transferred from hot to cold. So heat transfer will go this way. Okay, Q being the amount of heat that's transferred. It's transferred over this thickness 0.1 meters. And over the area 27 square meters. And we are asked to show that the heat transfer rate due to conduction is 5.5 kilowatts. So rate, okay, heat transfer rate, that means Q divided by time, right? Whenever you hear or you read the word rate, it means something divided by time. Heat transfer rate means heat divided by time. And the answer should be 5.5 kilowatts. So kilo, prefix kilo is 10 to the 3. Okay, so that means 5.5 kilowatts also means 5,500 watts. Okay. Multiplying with 1,000 or 10 to the 3. Right, so it explicitly says heat transfer by conduction. So we have Q and it says rate. So Q over T is equal to Ka delta T divided by the distance or the thickness. Yeah. Okay, and it turns out we actually have everything from the given information. So there's some other useful information at the bottom of the worksheet. The thermal conductivity of ice is given 2.25. So K is 2.25 watts per meter Kelvin. It times the area. So it's over the whole 27 square meters of area that heat is being transferred by conduction. times the difference in temperature. So difference in temperature, it's the hot minus the cold temperature. Okay, so you have 4 degrees minus -5. So don't forget to include the negative signs if there are any negative signs in the temperatures. That gives you a temperature difference of 9 degrees Celsius. Okay, that is of course equal to 9 Kelvin because you're getting the delta T, difference in temperature. So difference in temperature is 9 Kelvin. We'll use Kelvin just because the unit for the thermal conductivity of ice is given in kelvins. But okay, divided by the thickness. So the heat will be transferred over the thickness of the ice, right? As it moves from hot to cold regions, it will have to pass through this 0.1 meter thick ice. So D thickness is 0.1. Plugging everything in your calculator gives you this number 5467.5 watts, which you can round to 5,500 watts as indicated in the problem, which says show that the heat transfer rate is 5,500 watts. That means your answer should be what's given in the problem, 5,500 watts. All right. Okay, so as usual, feel free to type your questions. So symbol for the heat transfer rate, is it P? In a way, P is also watts, right? Power. Yeah, P is also power, which in a way it's also heat transfer rate, but power can also be used for electricity. So for heat transfer rate, we'll just use the symbol Q over T. I don't think we'll use power anywhere else. When we go to sound, we will also use the power P. Yeah, you're welcome to use P, power, for the symbol of heat transfer rate, but it's clearer to use Q over T so that you know that it's heat that's being transferred. So I would suggest just use Q divided by T for heat transfer rate. Yeah, but you're right that heat transfer rate can be represented as power as well. Cool. All right, so the next question says calculate how many hours, so that's now the time, it takes until an amount of 9.5 times 10 to the 7. So yeah, please correct that. That's 9.5 times 10. It's exponent 7. Joules is lost to the environment. So joules, that means that's a unit of heat. So that means Q is equal to 9.5 times 10 to the 7 joules. Okay. And hours is, of course, time, which is what we want to find. Time. Right. So what do we know and how do we solve this question? So from the previous problem, we've determined that heat is being transferred at a rate of 5,500 watts, which means that 5,500 joules. Let's just use the unrounded one. I think, let me see. Yeah, let's use the unrounded one so we don't have rounding errors. Right. So heat transfer rate, or the rate for which heat is transferred, is 5,467.5 watts, means that 5,467.5 joules of heat is being transferred every second. Okay, so that's where the time comes in. Yeah, in the rate, or in the watts. 5,467.5 joules of heat is transferred every second, and we want to calculate how long it takes to transfer this amount, 9.5 times 10 to the 7 joules, right? Okay, so you know the rate. You know the rate, Q divided by T. You want to find T. Right. So Q over T, we found that as 5,467.5 joules per second. Okay. And we want to find T. Right. So to find T, we need to isolate T. Okay. If we multiply both sides with T, then we get rid of T because you have 5,467.5 times T. So T disappears on the left side. And we want to isolate T. Let me just do the rearranging by flipping first. I think it's simpler. So flipping. Because we want to isolate T, and T is at the denominator. So it's easier to do T. I feel it's less confusing. Of course, you can rearrange it anyway, as long as it's correct. My iPad hang for a moment here. Come on. So T over Q, 5,467. 1 over 5,467.5. So all I did was to flip the equation, just so I can isolate T by multiplying both sides with Q. Okay. That allows me to cancel Q on the left side, and T will be equal to Q divided by 5,467.5. Yeah. Yeah, it's okay to calculate it using the whole equation. You'll find the answer will still be the same. Yeah. So the amount of heat that you want is 9.5 times 10 to the 7 joules divided by, the rate 5,467.5 will give you a time. This one will be 17375.4. The unit here will be seconds, right? Because the unit you had for 5,467.5 is joules per second. And so if you calculate the time, it will give you a time in seconds. Okay, but the question says how many hours? So you need to convert this to hours. Convert to hours by dividing by 3,600, because there are 3,600 seconds in 1 hour. So your time will be 4.8 hours, or about 5 hours. Yeah. Good. Cool. Right. Next question. So assuming all the energy goes into freezing more water, so the energy lost, meaning from the previous question, this 9.5 times 10 to the 7 joules. So energy lost, 9.5 times 10 to the 7 joules from the previous question. That's the amount of energy that's lost. Right, assuming that all of that energy goes into freezing more water, determine the increase in the thickness of the ice layer. And there's a hint here. The hint is that first you need to calculate the mass of the water that will be frozen as a result of losing this energy. Okay, so let's do that step by step. So the water here, it's at 4 degrees Celsius. Let me just write this down here again. So the water underneath is at 4 degrees Celsius. And so we need to freeze this 4 degrees Celsius water in order to add to the thickness of the ice layer. Last time we learned that this 4 degrees Celsius water will not freeze instantly, right? If you look at the temperature, how the temperature changes as the water loses heat. Okay, you start with 4 degrees Celsius. You start with 4 degrees Celsius water, and as the 4 degrees Celsius water loses heat, of course, the temperature will change. And so the temperature of that water will decrease as it loses heat, but it will decrease until its temperature reaches 0 degrees Celsius, right? Okay, so initially water with temperature of 4 degrees Celsius will lose heat. Okay, as a result of the heat being lost, its temperature will decrease up to 0 degrees Celsius. When it reaches 0 degrees Celsius, that's only when the freezing happens. Okay, and so your water freezes at 0 degrees Celsius. So it's a two-step process. The first process is when you're changing temperature. So you have Q is equal to MC delta T. Okay, amount of heat lost Q goes into changing the temperature by 4 degrees Celsius or 4 Kelvin, right? So delta T is 4 degrees Celsius or 4 Kelvin. Yeah, because your water temperature needs to go down from 4 degrees Celsius to 0 degrees Celsius. And then that's when all of your water is at 0 degrees Celsius, that's when you can have freezing. So you have the phase change, Q is equal to ML, as the water freezes at 0 degrees Celsius. Okay. Right, so you have this two-step process. So the total heat lost Q goes into changing the temperature, Q equals MC delta T, plus changing phase, Q is equal to ML. Right? You're freezing, so that will be fusion, ML fusion. Right, so it's the same mass, it's the same amount of water that changes temperature, that goes down to 0 degrees Celsius and also freezes. So the mass is the same here in these two terms, so you can factor out mass. Okay, I think we learned about factorization before. And so you can take out mass from both terms in the equation. So you have mass times the thing in brackets. Okay. So that's what this hint comes from. That's where the hint comes from. Q is equal to mass times C times 4 plus L. A change in temperature, this change in temperature is of course 4 Kelvin or 4 Kelvin. Okay. C is the specific heat and L is the latent heat of fusion, LF. And the hint actually calculated the whole thing for you already. So the whole thing in brackets because it's just constant. So you have C. So if you calculate what's in the bracket, you have C is given here, 4182 times 4, the change in temperature, plus the latent heat of fusion is also given 3.34 times 10 to the 5. Okay. So it's this brackets that's being added. Yeah, you will have mass times 3.5 times 10 to the 5, which is what was given in the hint. So that's how the hint was derived, but you can just use the hint to solve the problem now. Okay, so before we proceed further, does that make sense? How we have this equation that was given in the hint? Okay, good. Right. So this Q is equal to mass times 3.5 times 10 to the 5. Okay, so assuming all of this heat Q goes into freezing water, we have this relationship. Q here is the amount of heat lost. And that's equal to 9.5 times 10 to the 7 joules, because we assume that all of the heat lost goes into freezing water. Then the only thing we don't know here is the mass. So find mass. Yeah, right. So we rearrange that equation to isolate mass. We'll have Q divided by 3.5 times 10 to the 5, times 10 to 5. Right? Okay, so to isolate mass, we need to get rid of 3.5 times 10 to the 5 on the right side of the equation, and we do that by dividing both sides with 3.5 times 10 to the 5. So we can calculate the mass. 9.5 times 10 to the 7 divided by 3.5 times 10 to the 5 gives us a mass of 270.865 kilograms. Right? So we know the mass. How do we know the thickness? Okay, because that's what's being asked ultimately. Determine the thickness, the increase in the thickness of the ice layer. So we know that this much ice, this much water will freeze into ice. How do we convert this mass into thickness? Okay. Right. So the only way we can relate mass to thickness is via the volume of the ice that's frozen. Okay. And the volume is related to the mass via the density. So recall that density rho, density is equal to mass divided by volume. Okay. And so we can rearrange this to find volume. Volume is equal to mass divided by density. Okay. So by using the density of ice, we can solve for the volume, and we're given here, we're given the density of ice. It must be somewhere. Otherwise, we can just search it in Google. density of ice is equal to 920 kilograms per cubic meter. Right. Okay, so we know how much ice how much water is frozen into ice by calculating the mass, and so the volume will be 270.865 kilograms of ice divided by the density 920 kilograms. Kilograms per cubic meter for the density of ice. So we can find the volume to be 0.2944 cubic meters. So as long as you're checking that your numbers are using standard or SI units, then you can be sure that your resulting units should also be in SI or standard units. So that will be cubic meters for the volume. Right. So how does the volume translate to the thickness? So if we draw, right, the sheets of ice, okay, the volume of the sheet of ice is the area times the thickness or thickness of the ice. Right. Okay, so that's now how we will be able to find the thickness of the layer of ice that's added by knowing the volume. So the volume, in short, is equal to the area times the thickness of the ice. Okay, so rearranging this, dividing both sides by the area, because we want to isolate the thickness is what we want to find. Right? So the thickness will be equal to the volume divided by the area of the surface. Okay, the volume we've calculated to be 0.2944 divided by the area of the ice, the sheet of ice. And that was from the previous question, 0. No, what's the area? 27 square meters. Right. Gives us a thickness of 0.01 meters. Right. Yeah. So it's quite a complex problem involving many concepts. So first key point is, to freeze water. Water needs to go down to a temperature of 0 degrees using Q equals MC delta T, and then you have the freezing itself, Q is equal to ML, and the combined heat lost for that process is 9.5 times 10 to the 7 joules, which is Q. And from there, we can find the mass of the water that's frozen into ice. We assume that the mass of water is the same as the mass of ice. So we've found here the mass of the frozen ice, okay, 270.865 kilograms. By knowing the mass of the frozen ice, we will be able to figure out the volume of the frozen volume of the ice by using the density of ice, which is just a constant number that you can search in Google or look at tables. So by knowing the volume, 0.2944 cubic meters, and looking at the geometry of the ice sheet, the volume is equal to area times the thickness, and therefore we're able to find the thickness, which is 0.01 meters. Okay. Right. So it takes a lot of, it's quite a complex. I would say that this type of question is probably more complex than what is expected in the exam, especially for a multiple type question in the exam. But this shows us, how we can combine all the concepts that we have learned so far. So when you're looking at a problem, don't limit yourself to what we've just learned in the particular lecture. If needed, also expand the concepts to previous concepts that we have learned. Okay, right. And for the last question, as I've said, we'll talk more about this tomorrow because it involves evaporation, but we can already answer this using what we learned today and the previous lecture as well. So here on a hot day, evaporation from the pond. So evaporation is a phase change, essentially going from liquid to gas. So you have Q is equal to ml vaporization, going from liquid to gas. So evaporation has just enough heat from the pond, has just enough heat transfer to balance the 1 kilowatt per meter squared of incoming heat from the sun. Okay, so the scenario there is you have the ice layer of ice on the pond. Okay, the area is 27 square meters, so we assume that. So you have the sun shining on the pond. Okay. And as the sun is shining on the pond, it transfers 1 kilowatt per square meter on the pond. So you have Q over T, 1 kilowatt per square meter. So prefix kilo means 1,000 or 10 to the 3. So that's essentially 1,000 watts per meter squared, or 1,000 joules of energy is transferred per square meter of the ice every second, right? So essentially watts means joules per second. So that means 1,000 joules of energy is transferred every second to an area of 1 square meter. That's essentially what this means. This 1,000 kilowatts per 1,000 watts per meter square means 1,000 joules of energy is transferred every second over an area of 1 meter squared. Okay. So if we write that in equation form, Q over T is equal to 1,000 watts over meter squared. Okay. Now, but what we want to find is the mass of water that evaporates every hour. So in evaporation, you have Q is equal to ml. We want to find M. Okay. So to find M, we need to figure out Q, right? L is just a constant, which is this latent heat of vaporization. It's just a constant number. So for us to figure out what mass is, what M is, we need to figure out what Q is. Q is the amount of heat that's transferred in order to evaporate the pond, evaporate water from the pond. Where will we find Q? We can find Q from here. We know that Q over T is equal to 1,000 watts. We want Q, we don't want T. So Q, we have to then multiply that with T. Yeah, 1,000 joules is transferred every second, means that we need to figure out how much Q is transferred in 1 hour. In 1 hour, yeah? The problem says 1 hour of time. So how much Q in 1 hour? Or 1 hour is 3,600 seconds. Right? So that's 1,000 times 3,600 seconds. Gives you 3.6 times 10 to the 6 joules. Okay. Yeah, we assume that it's transferred over 1 square meters because you have here a meter squared. So how much is transferred over an area of 1 square meter? Right. Okay, does that make sense? Because I think yeah, all right, good. So once you know how much Q or how much heat is transferred over that 1 hour, then you'll be able to find the mass of water that evaporates. Yeah. So to find so rearranging that to isolate M, divide both sides by L. So you have Q divided by L. And it's LV or L vaporization because the water evaporates. Right. So you have mass is 3.6 times 10 to the 6 divided by LV is just a constant number, 2.46 times 10 to the 6. 1.4646 kilograms. Right. So the idea there is the sun transfers heat onto the surface. Okay. The sun transfers heat onto the surface at a rate of 1,000 joules every second for every square meter. Okay, and as a result of that amount of heat, we'll start again. So the scenario is the sun imparts heat on the surface at a rate of 1,000 joules every second. So over the duration of 1 hour or 3,600 seconds, the amount of heat that's transferred by the sun is 3.6 times 10 to the 6 joules. And this amount of heat transferred by the sun is used to evaporate the water in the pond. Okay, and so the mass of water that's evaporated was determined using this equation, the amount of heat transferred divided by the latent heat of vaporization, giving us a mass of 1.46 kilograms of water being evaporated in an area of 1 square meter. Does that make sense? Does the solution make sense? Yeah, all right. So we will look more into evaporation in the next in the next lecture. Yeah, but here we've seen that evaporation is essentially a change in phase where you have Q is equal to mL. All right. So are there any questions related to the workshop or the lecture or otherwise, just before we end this workshop session? Right. Okay. Just watching the chat box. I don't see any questions. Right. So I think, yeah, there's a question. Yep. Oksana.
Sorry, it's easy to unmute. So to calculate the general amount of water from the pond, we will need to multiply this mass of water by 27. Is it correct?
That's correct.
Yeah.
That's correct.
Thank you.
Yeah. Yeah. Yeah, because this 1.46 is just over 1 square meter. You're right. Yeah, you're actually right there. So for 27 square meter area of the pond, total mass times 27. Yeah. $39.42 kilograms. Yeah. Good. Right. Any other questions? Right, no more questions. Okay, good. All right, thank you for coming. And I wish you a great day, everyone, for the rest of the day, and I'll see you again on Friday. All right.